Every direction you point a microwave antenna, you receive a faint hum of radiation. It is cold, 2.725 Kelvin above absolute zero. It is uniform to 1 part in 100,000 across the whole sky, and it has been on its way to us for 13.8 billion years. The signal is called the cosmic microwave background. Arno, Penzias, and Robert Wilson, two radio astronomers at Bell Laboratories in Holmdel, New Jersey, first detected it in 1964. They were calibrating a 20-foot horn-reflector antenna for a different project entirely, and working to eliminate every local source of noise. The noise they could not eliminate arrived from every direction of the sky, across 9 months of observation, with an excess antenna temperature of about 3.5 Kelvin above what their instrument should have registered. Their paper appeared in the Astrophysical Journal in July 1965. In the same issue, a companion paper by Robert Dicke, James Peebles, Peter Roll, and David Wilkinson at Princeton University, 50 kilometers away, provided the interpretation. Their group had been building a dedicated antenna of their own. They had been looking for this exact radiation, predicted in the 1940s by George Gamow, Ralph Alpher, and Robert Herman as the thermal remnant of a hot, dense early universe. Bell Labs had found it first, by accident. 13 years later, in 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for the discovery. The radiation comes from a specific moment in the universe's history. For its first 380,000 years, the universe was a plasma, hot, dense, and opaque. Photons could not travel freely. They scattered off free electrons almost immediately after being emitted. Then, as the universe expanded, it cooled to about 3,000 Kelvin. At that temperature, protons and free electrons combined into neutral hydrogen atoms for the first time. Scattering stopped, light could cross space unimpeded. The photons released at that transition, called the Recombination era, have been traveling outward ever since. Every microwave photon reaching an antenna on Earth today was emitted in those same few moments. The wavelengths were visible when they left. The expansion of the universe has stretched them into the microwave. The second remarkable fact about the CMB is its uniformity. Across the full sky, its temperature varies by only 1 part in 100,000. That degree of smoothness is a strong constraint on physics in the first moments after the Big Bang. The best explanation requires that the entire observable universe was once in thermal equilibrium across a region now far larger than the speed of light could have crossed. The leading account is cosmic inflation, developed by Alan Guth in 1980 and Andre Linde in 1982. A brief phase of exponential expansion in the first fraction of a second stretched one small equilibrated volume into the scale of everything we observe. The third fact turns the second one on its head. Those small departures from uniformity, the 1 part in 100,000 fluctuations, are not noise. They are structure. In 1992, the COBE satellite first measured them. WMAP in 2003, and Planck in 2013 and 2018 mapped them in fine detail. Every galaxy, galaxy cluster, and supercluster in the universe began as a slightly denser-than-average patch in that early plasma. Over 13.8 billion years, gravity has amplified those small differences into the cosmic web we now see. The fourth fact is what the measurements now tell us. The Planck collaboration's final analysis, published in 2020, set the age of the universe at 13.8 billion years to within 20 million years. It set the Hubble constant, the rate at which the universe is expanding today, at about 67.4 kilometers per second per megaparsec, though a persistent disagreement with local distance measurements remains unresolved. And it set the composition of the universe, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Everything we can see, the stars, the planets, the living organisms, is 5% of what is out there. The discovery itself, though, was accidental. Penzias and Wilson had not been looking for cosmological radiation. They were trying to build a sensitive receiver for radio astronomy observations, and the persistent hum they could not remove from the antenna was, to them, an engineering problem. They worked through every local source they could think of. They found nesting pigeons inside the horn and cleaned out what Penzias later described as white dielectric material. The hum remained. It was only after a telephone conversation with Dicke's group at Princeton that the signal acquired its interpretation. The same detection was independently confirmed, in precision form, in 1994 by the COBE FIRAS instrument, whose principal investigator, John Mather, would go on to serve as senior project scientist on the James Webb Space Telescope. The cosmic microwave background is the oldest light that can ever be seen. Earlier than the Recombination era, the universe was opaque, and nothing more distant than that surface can reach us. The hum that two engineers found in a microwave antenna in New Jersey is the edge of the universe's visible history. Everything else we observe lies inside it.